Good afternoon. Our today's speaker is Livia Lilli. Thanks for accepting our invitation. And Livia works in the wide and wide world of natural language, and today she's going to speak about real-world application of natural language processing in healthcare.
Yeah.
The floor is yours.
Thank you. Hi, everyone. I'm Livia Lilli, and I'm working as data scientist at the Gemelli Hospital of Rome. In particular, today I will present to you the real-world application of NLP in healthcare, specifying the MISTIC pipeline that is our latest work about the identification of metastases from clinical reports. Well, this is the agenda. So we will see a small introduction and methods of NLP in healthcare. Then we will move to the real-world use case, looking at the details of the MISTIC pipeline. And finally, we will discuss about the related works. So before going into the NLP, I would like to talk first about the real-world evidence. So the real-world evidence is a great concept in healthcare because it's the result of analysis and research that are done on the real-world data that are electronic health records, clinical registries, wearable devices, and all the data that comes from the digital apps. So real-world evidence is the object of the healthcare research, and here there are some definitions. So real-world data are all the clinical data about patients that come from electronic health records recorded into the hospitals, clinical registries, so datasets that are collected specifically for prospective studies, patient-reported outcomes, so all the data that patients insert into the digital apps for monitoring, and the wearable devices, so for example, smartwatch, smartphone, etc. This data can collected routinely, so for example, clinical reports that are written during outpatient visits or during the admissions of the patient, and can be a little bit noisy. So they contain errors, and they are not perfect. So they are not collected for a study, for a research, but just for the patient's monitoring. So they can be used in research, for example, in retrospective studies, but they need to be processed and clean for the scope. So here there are the respective studies that are research about the historical data of the patients. So here are used all the routinely collected data about the history of the patients. And usually we focus our attention on this kind of research. On the other hand, we have the data collected intentionally for a project. So in here we have some prerequisites. So for example, data must be clean, must be collected in a specific way, specifically in a structured way. And so this data can be collected for a specific prospective study just when the protocol of the study starts. So this is another kind of data with respect to the previous one, but it's more usable for research that can be supervised by protocol. And real-world evidence is the object of our research, in particular in the data science unit of Policlinico Gemelli Hospital. And why natural language processing? Because the real-world evidence needs data that not always are in a structured data mart. So for this reason, we need NLP models in order to interpret, but also to extract information from the clinical text that comes from discharge letters, clinical histories, radiodiagnostic reports, anatomy pathology, and also from outpatient visits. So all these textual data are our objective of study in order to apply and implement existing NLP approaches and to generate some structured outcomes about, for example, therapies, symptoms of the patient, all the historical events of the patients during the hospital admission. And this is a good method in order to make automatic extraction from the text to provide scalable solutions, but also to accelerate research because we are not collecting this data manually, but with models that can do this in few minutes. And this allows us also to improve the decision making because these data are then used for predictive modeling or for statistical analysis. So it's really useful for the research in the clinical field. Here there are some applications of the NLP. So we use NLP for text preprocessing and for information extraction. First, we usually do topic modeling, for example, by using frameworks or model like BERT topic in order to automatically detect semantical topics inside the clinical reports. But for example, we can also use the generative large language models in order to do text summarization. So for example, to produce a summary of the clinical report in order to make a shorter version of the report that can be more concise and easily processable by the models. We also usually build knowledge dictionaries in order to have a knowledge base for be used from the model in information extraction phase. So here, for example, with physicians, usually we build this dictionary of knowledge in order to have some context to give as input to the models. And finally, there is the sentence boundary detection. This is a very, very interesting technique because allows to segment the text into smaller paragraphs in order to make them shorter text, more concise, also here more processable by the information extraction models. On the other side, we have the information extraction. So here, for example, we have text classification tasks. So the models can categorize the clinical reports in specific classes, for example, present or absence of progressions or of metastasis. And we have also an entity recognition. So in here, we have models that can recognize and identifying the entities of interest. So, for example, treatments, symptoms, but also, for example, personal information about patients, for example, names, addresses, etc. And then in the middle, we have the text generation. So text generation is used in both the scenarios because, for example, in text preprocessing, we can use generative models to translate the text, for example, from Italian to English in order to use already existing English models for information extraction. Or, for example, can be used for text summarization and simplification. And on the other side, in the information extraction field, generative LLMs are used for generation. So we can ask, for example, to ChatGPT to extract some information. So it's a really mixed field that can be used in both the scenarios. Here there are some methods that are usually used in our real-world hospital application. So, for example, in the first years, we used a lot the pattern matching that physicians love in a particular way because it consists in building rules in order to extract specific information. So in here, there is the manual drafting of the rules in order to extract data based on patterns, based on distances among words, or for example, based on the structure of the sentences. And so this is really interesting because it requires a high manual effort, but it works very well and it's explainable because physicians can understand why the system return a specific output. These systems are also used for sentence boundary detection because we can also use, for example, the system to segment text based on the presence of specific patterns. But for the negative aspects of this approach, we usually move also to transformer. Transformer architectures are really used and famous in these last years because they are deep learning architectures that are specifically based on the presence of the encoder, but also on the decoder. And they are available in their pre-training version, so we can use the pre-training of these models that are pre-training over billion of parameters, and they can be adapted on specific domains. So, for example, we can use a BERT model and fine-tune it on a specific clinical domain or on a specific language, for example, the Italian. And these approaches are more generalized with respect to the pattern matching, and they require a lot of annotation because we need large training set for the fine-tuning of this kind of models. Lastly, we have the generative large language models that are usually based just on the decoder of the transformer architecture. And also here we have available the pre-training on billions and billions of parameters, so they are very large, as the name say. And the adaptation can be instruction tuning, so also here large training sets that are used to train the model in order to respond to specific instruction. And also lightweight solutions like the in-context learning and the few-shot prompting. So in these cases, we can use this kind of models, prompting them, so asking something to this model like ChatGPT, and inserting in the prompt some context. So for example, dictionaries, examples, and so on. So it's a lightweight and less technical way to adapt this kind of architecture. And well, now we can move to the next, that is a detail of each approach. So the pattern matching that is the easiest one because takes as input text. We build the rules that can be regex, that can be more personalized rules about distances, about structure of the sentence of the text. And the output is the identification of information, the segmentation of a text. But as I said before, this is highly accurate, highly explainable, but it's not well generalized over multiple data sources, because if I build the rules on a specific kind of report, this system will not work on new data. And it requires an high manual effort, so it's not always the best solution for our purposes. For this reason, usually we move to the transformer architecture, that is a deep learning model released in 2017. And this model replaced the state-of-the-art models like...
Sorry. Yeah? So what is the pattern? Can you say that the pattern is just a portion of string that obeys some rule?
Yes.
It's just that.
Well, patterns are keywords or expressions that can be found inside the text. But this search can be also combined with specific rules, for example, based on distances among these expressions, based on, for example, the presence of other symbols.
So you basically fix a string and then you ask yourself whether the string is far enough in some distance, maybe the distance, something like that. From
Yes, we can say this. Usually we build dictionaries with physicians. So, for example, a list of expressions and of keywords for find, for example, the concept of metastasis.
So
and
the
then
is, when you run a pattern matching algorithm, what are you doing? Just searching
specific strings inside the text, but also searching if there exists a specific rules that is satisfied. So, for example, can be just a search of a word, but can be also a search of a word that must be
in some manner.
Yes, exactly.
Thank you. And what does it mean autoregressive?
Autoregressive method is an approach that is used in the pre-training of large language models and transformer architectures.
In this context?
In this context, it's not used in the pattern matching field.
No. In general, in natural language, what does it mean?
Autoregressive. Yes, the prediction of a next token based on the previous one generated. And it's usually a technique used for the pre-training of large language models like and transformer architectures like BERT and Llama and the other large language models that are really famous today. So this
mathematically, it's a very well defined question. But if you don't define mathematically, autoregressive is not easy.
Yeah, we can say that in the NLP domain, Yeah.
Yes, maybe she puts some distribution on the, on what she has seen so far, and then try to forecast the next spring, maybe.
Yeah.
Something from a dictionary. I guess. But it's not my
Maybe it's not the topic of the seminar, but it's a bit complicated because mathematically speaking, you can think some Markov chain model, but if you try to compute it, no way. You need to spend maybe
just
century of years.
Just understand the mathematics. You are building a Markov chain of portion of string?
No. Because it's not computationally working. People try to do some Markov chain approaches, but the implementation takes years. Okay.
But why you put autoregressive among the features of
the other
it's
model?
Just
Of the other model.
Of the other model.
Of the other models, of the transformer and the generative LLM. Yeah.
If you require that, I think you need they should be autoregressive or not.
But the first point is to quantify the homogeneity.
Yes, but I can guess what is autoregressive. If you try to build a Markov chain
to define something Markov, you must have quantified.
Of course,
you cannot quantify these homogeneous quantities.
No, but I think they have some transition.
No, you need just to change minds. You have a lot of textual data, okay? Maybe a lot of sentences. You want just to take the beginning of the sentence, 3 words, and you want to predict the fourth.
Yes,
okay?
I see this. This is a Markov chain.
Yeah, but when people, it's not the topic of this seminar, okay? But when people try to do it with a Markov chain model and they try to compute it, it's impossible to do a system like that in human life because of the dictionary, 300,000 of words, okay? A billion of combination. Then with deep learning techniques, people started to do some not so mathematical things, a lot of computational architecture, and they are able to do that. Because people working on that call it autoregressive. Okay? It's just a semantic misunderstanding. People working on that calling it autoregressive. Okay?
And from the formalization perspective, are these entities like kind of multidimensional vectors, or are they something different?
Yes, usually now we will see in detail how the transformer process the text, but usually the words are encoded into tokens that are then represented in embeddings vectors. So are processed in order to make them eligible for the LLMs. So maybe we can also go on and see some details.
Thank you. Sorry.
No problem. It's just a way where we define the technique on which we pre-train this model. And usually we don't make pre-training because it's really expensive computationally, but we use already pre-trained models that are available, for example, open source, adapting them for a specific domain. So usually the pre-training is not done by us, but we use and leverage on existing pre-training models. And looking at the transformer, the real novelty of this kind of architecture is that these models process the data in parallel, and in particular, the main components are tokenization, positional encoding, self-attention, and the encoder-decoder architecture. Before going on with these components, we can also say that the transformer process all the sequential data. So we are just talking about text for our use case, but there are, for example, also code, time series, molecular data, images, and audio that can be processed by this kind of models. So now there is the tokenization. The tokenization is a process that...
I have a semantic difficulty.
Yeah.
Because you are using as evidence, in the sense common language,
Yeah.
words like molecular. I mean, it's molecular in something very specific. Now, in this set of data, very either you define to me the specific meaning which you are using this concept, or I have lost.
Okay.
Maybe this is about molecular sequences.
Yes,
It's not-
exactly. Yeah. Sequential data.
Whatever word, if you go back to the transparency, almost every word is, to me, time series.
Yeah.
Everything is a time series, but it's not true. A time series normally is the evolution of a phenomenon well characterized, vectorial, scalar, but I mean, cannot be a set of different shoes, cannot be a time series.
No, but Giovanni,
So-
you can build a stochastic process in whatever state space you like. The time costs are not real number, head on or so you can do this on strings.
If you don't use the common sense, you must define what you are doing. And
Yes,
here,
yes, of
I
course.
am in difficulty in following you,
Mhm.
because you seem to use common sense words, but clearly they are not common sense.
Okay.
Okay.
Yeah.
So
Yes, but you need to. Sorry.
Yeah, not just it's just an overview to show that this model can be adapted also on different kind of data. Of course, this seminar is focused on the usage of these models on textual data, but there are several researches that also focus the usage of these architectures on other kinds of data that we didn't use in our research, but that there exist in the NLP world of the research and of the industrial research.
So we
it's
do
just-
appreciate that the word sequential data is a bit of a broad category, but gives you the idea of what is common among these use cases, which is a sequential approach to entities, which in the case of language are strings of words.
sequential data intuitively means there is some causal connection in
Yeah.
between.
No, it's more general. This one is just a slide to have an idea that this kind of model and architectural and algorithms can be used in other fields, okay?
Right.
Then if you want to do an insight on molecular data and molecular approaches of transformers and deep learning in the field of molecular data, maybe we need to do another seminar to explain which kind of molecular data and so on. It's just to have an idea that this kind of architecture can be used on other fields like text and other tiny text.
It's more used than causal connection, because I mean, if you have a sequence of words, the roots are coming from semantics and not coming from causal in the sense of a physics.
If they are completely causal, they are completely different.
Okay, of course, but
Yeah.
there is no semantics behind it.
Sorry, guys, this very well fits the purposes of this seminar, but I think you should go on.
Okay.
Yes,
of course. Well, the tokenization allows to these models to encode the words into tokens that are the base unique units of the transformer architecture. And from the tokenization, we can define the context length, so the maximum number of tokens that the model can process, and the vocabulary size, so how many tokens the model can recognize and process also as output. The tokenization can happen at 3 levels, so at word, subword, and character level. And once the sentence or the text is given as input to the tokenizer, the tokens that are generated are then given as input to the large language models, passing through the second component, that is the positional encoding. So here, in particular, the tokens are given as input to the LLM, and at first they pass through the embedding layer. So in here, the tokens are encoded into embedding vector, And the embedding vectors are then passed through the positional encoding layer, where the information about the position of each token is added. This why it's a good question, because the transformers process the input data in a parallel way. So they lose the information about the token's position that is recovered in this positional encoding layer. And then I'm going also very fast on the self-attention. That is a really core component of the transformer, because in here, for each couple of tokens is computed an attention score. That means the level of dependency of this couple of words. And in particular, this process can be also repeated multiple times. So it's called multi-head attention. And at the end of this process, usually we have an attention matrix that is then multiplied with the embedding matrix in order to get a weighted representation of the embeddings, where also this information about the dependency of the tokens is encoded. And finally, this is the architecture. So another peculiarity is that the transformers are composed by encoder and decoder. So the encoder takes as input the tokens and return the embedding representation of these tokens. Then this output is taken as input from the decoder that generates other tokens. Usually exist models that present just the encoder part, making then text classification or NER, for example, by adding a classification head over the network. And there exists also decoder-only models. So, for example, the LLMs are usually based just on the decoder part, and usually they make text generation. And finally, we have also models that present both the encoder and the decoder parts. In these cases, models can also make, for example, tasks like text summarization, text translation, and so on. And in particular, here there is an overview over time of the most famous. These are really few because we have a lot of transformer models, but yeah. For example, in 2018 was released BERT, that is the most famous transformer architecture that exists. Then we have clinical BERT and distil BERT that are derivatives of BERT, specifically trained, for example, in the clinical domain, or there is the distilled version. And these are just encoder-only models. When in 2019 was released the GPT-2, for example, this model is a representation of a decoder-only transformer that is not already a large language model, but it's near to be a large language model. And then we have the T5 that was released in 2020 that present both the components. And in particular, starting from this, we then can talk about large language models. So what are the LLMs? They are based on the transformer architecture, but during pre-training and during the pre-training are trained over millions of parameters. So they are very large and computationally expensive to be used in a real-world settings. For this reason, we usually use a quantized version in order to make easy the usage of this kind of techniques. And the main characteristics are parameters, so the count of the trainable weights that are used during the pre-training of this model, the context length, so again, the maximum number of tokens that can be processed as inputs, but with respect to the old transformer architecture, the context length now is higher, and the model size, so the number of bits of occupation of this model on the machine. Some examples, few examples again. For example, in 2025, the most famous LLMs that were released are Gemma 3, GPT 4.1, and DeepSeek. These are more general context models, but for example, we have also Gemma and Minerva that are domain-specific models, in particular pre-trained respectively for the medical domain and for the Italian language. So, for example, Minerva was released by Sapienza. And these are really interesting because we have both the situations, so more generic models that can be used in any context, and domain-specific models that work very well in specific languages or domains. For the Italian, Minerva is used, but also multilingual models like Gemma, like Llama, are used for real-world application in the Italian language. So, for example, we usually use also Llama, Mistral for our purposes. And about GPT, we can use it, but not on the clinical data because of privacy concerns. So, for example, we use GPT in contexts where we can accelerate research, for example, in the construction of systematic literature review. But for clinical data, we have the need to use local models, so models that we can download locally and use in our machines. Well, now the question is when we can use transformer architectures like BERT, or we can move on large language models. We have seen some differences, so in terms of architecture, in terms of size and pre-training again. But the real difference is the adaptation. For example, the transformer can be used in an adaptation way when we have a large training set for make fine-tuning. On the other hand, large language models can be adapted to the instruction tuning. So here, if we have a large training set for instructions, we can adapt this model in a massive way, but we can use also these models with lightweight adaptation techniques like few-shot prompting and in-context learning. And the really interesting thing is that this kind of prompting techniques allows also less technical user to use this kind of models. And the use case is similar in the sense that transformers are usually suitable for text classification, NER, and question answering, while large language models are suitable for text generation that can be adapted to a text classification task. About the resources, while large language models are really large and so really high computational demanding, transformers can also be used in a moderate computational setting. So the choice is not unique and there is a best choice. There is the choice that can be made based on the task, on the computational resources, the time. So if we have the time to annotate the training data, we can make fine-tuning or instruction tuning, and the knowledge domain. Well, now that we have seen an overview of the NLP, we can talk about MISTIC. MISTIC is a research that come from a request, so the identification of breast metastases from clinical records. Why? Because this information in our hospitals are not available in a structured way. So we needed a technique to extract this information automatically from the text. The request was to find a lightweight solution for be applied in a real-world setting, to reduce the manual annotation for the training set, and also to keep the model explainability for physicians. So in order to understand why the model classify certain clinical reports in a category. And then we have our latest paper with Mario Santoro, so the collaboration with the IAC. And in here we have developed a pipeline for the identification of metastases where preprocessing and modeling are combined in order to find a solution to this aim. So the input data. The data are coming from 3 different data sources. So we use the clinical diaries that are a set of clinical events that are reported in the text during, for example, the admission or the outpatient visits. Clinical histories that are very, very long reports where all the history of the patient is reported, and the radiodiagnostics. So all the textual reports that talks about results of imaging. So in here we try to represent each data source in our training set in order to make the model well generalized over the multiple data sources. And these data were the input to the sentence boundary disambiguation. So the very first step of our pipeline was to segment the text into smaller segments by using PySBD, that is a Python module for the rule-based sentence boundary disambiguation for the Italian, also for the Italian language. And before the segmentation and after the segmentation, we can see that the tokens per report and the tokens per sentences are decreasing a lot. And this was really useful to comply with the context length of the BERT model that we use for classification. And then we also perform a topic analysis in order to analyze all the possible way in which the metastasis can be expressed in text, because we don't have always the word metastasis inside the text. The metastasis can be also expressed in other ways. And for this reason, with physicians, we build a dictionary of all the possible expressions, and we analyze the distribution of the most frequent semantical categories that are on the right. In particular, metastasis can be defined with the concept of high metabolic activity, lesion, metastasis, nodule, and also inside the definition of the TNM staging, that is the staging that usually is used by physicians to express the status of the breast cancer. In particular, in here, what we did was to filter the segments by keeping just the ones that contain the information about metastasis. And we also built the training set that such that was balanced not just over the 3 data sources that we have seen before, but also over these 5 categories. So in order to train the model to understand the possibilities of the metastasis expression. And about the modeling part, we can pass through this slide where it's explained that we used a sentence transformer, so an architecture that is able to encode the sentences and not the entire text. In particular, we leverage on the set-fit framework that it's able to compute the embeddings based on the similarity among the text and a query vector. In our case, the query was presence of metastasis, written in Italian, and this framework is able also to work in a few-shot learning setup that allows us to use really few data to train the model. That is a novelty for the transformers. So our training set was composed by 500 of text segments, and that were annotated with the presence of metastasis by physicians. And in particular, these are the results. So about the results, we first trained the model on 2 setups, so using 550 samples and 1,100 samples, finding that the smaller training set was the one that returned the best results. In particular, we also find that over all the 3 data sources, the model can achieve an high F1 score. So this is also the proof of the generalization of our model, of our approach over multiple data sources. But we also try to compare our approach to other state-of-the-art models in the NLP research. So at first, we compare it with a rule-based system. So here we find patterns and keywords to search inside the text, looking at, for example, distances, presence of negations, etc. So in here, we compare our approach to the rule-based system, finding better performances in MISTIC. Then we use the zero-shot learning models. So in particular, we choose among BERT-based models that could be used in a natural language inference setup, so with not training. Then we use the structured generation. So, for example, we leveraged on generative large language models like Llama, Minerva, and Mixtral by using them in a structured generation framework. So asking to them to return binary outputs, presence or absence of metastasis. And then the set-fit framework was used over multiple sentence transformers in order to compare different models. And we found out that the best model that we used was then integrated in the MISTIC pipeline. And these are just quantitative results, but we have also analyzed qualitative results. So we found that MISTIC require few data for training, is explainable because the segmentation and the filtering by topics of the segments are able to easily identify which segment of the text of the clinical report triggered the classification. So it's also easy to explain to physicians why the model return a certain classification. Then this approach was also well generalized over multiple data sources, and this was achieved with the previous results. This approach is computational demanding? No, or moderately, in the sense that we use it in a machine without GPU, that is in the NP scenario is a novelty, and the automation is full. I mean, we just annotated the training set and the evaluation set for making the results, but it's not as, for example, in the rule-based scenario where we have to build the rules, find the patterns that are most readable with precisions, etc. So the MISTIC pipeline is also a good balance among all the characteristics in a qualitative scenario. So now what we did was also to find out similar researches that focused on the usage of large language models and BERT-based models for information extraction in the clinical field. In particular, in this last work that was released in 2024, generative LLM were compared to masked large language models for NER task in several languages, so Spanish, English, and French. And
yeah, sorry, can you explain what means NER?
NER is, sorry, we have seen it in the latest slides, it's name entity recognition. So it's the identification of specific entities inside the text. So for example, treatments, symptoms, all the entities that are of interest for the research. And for example, in IR, they found out that the BERT-based models outperform the large language models in the low resource settings. So these findings are similar to the ours. Then there is another work, always about the benchmarking of LLM approaches, in particular here over retrieval methods like chain of thoughts and RAG systems. And in this work, they found that there are several limitations in the usage of these approaches for classification and name entity recognition tasks. But on the other hand, we have also works that have opposite findings. So for example, here they find that GPT-4 used for structured generation is really performing with respect to fine-tuning a BERT model. And again, another work find that task-specific prompting can be used for name entity recognition tasks and can be of higher performances with respect to more traditional models. So also here, it's confirmed that there is not the best solution ever, but it depends on the task, the use case, the data viability. There are a lot of factors that can contribute to the best choice of the approach for a specific project. And here there is also another use case we worked on, and in particular the lupus use case, where we have to identify the main lupus features from the clinical reports, because also here the features were not available in a structured format. And in particular, we start with the pattern matching, then we pass to the fine-tuning of a transformer model, and finally we also experimented some large language models in order to see if there could be a potential solution. And in here are represented all the features that we extracted. In particular, we focused on the identification of 8 different diagnoses, 21 symptoms, and 4 different macrogroups of therapies. And in particular, with the results, we found that the pattern matching is the most performing approach over all the 3 domains. And it's highly explainable because the physicians built the rules with us, so they know how and when and why the patterns are found and why the extraction is performed. But it's not generalized, so if we use this system on new data of another hospital, it doesn't work, and it requires an high manual effort. So we pass to the transformer approach. In here, for example, we have slightly lower performances, but a good explainability and a good generalization of our new data, because thanks to the control that we can have on the training data. And these are just preliminary results. I mean, with a better training, maybe improving the training set and the dimension of the training set, we could also achieve better performances. So there is a great potential for this approach. I think that we could also going on with the research on this field. And finally, we also try large language modeling. So in here we just focused on the diagnosis task, comparing two scenarios. So we used the zero-shot prompting, just asking to the models what is, there is an articular diagnosis. And then we also make in context learning. So in the prompt, we gave to in input also the context. So for example, a dictionary of words, some examples. And here we found that in the in-context learning technique was really performing near to the transformer. Also here we have preliminary results, so improving the prompting, or for example, moving to an instruction tuning adaptation technique, we could also improve the performances. And as I said before, the large language models has a great potential also for be used in a no technical scenario with physicians that could prompt the models in order to find information. Well, this also is a fast overview of another breast use case, always implementing NLP for identifying breast cancers. In here, for example, we use the large language models and for preprocessing, so we perform text summarization. And then in the modeling part, we compared the instruction tuned llama, a fine-tuned bird model, and we also try to ensemble the two models in a final approach, comparing the results. In particular, we find that in the summarization task, with summary, we got shorter segments of text, more concise, about the information of metastasis. So it was useful in order to comply with the context length of the llama model. On the other hand, we can see that both the transformer and the instruction tuning of llama return more or less good results, and the ensemble returns more balanced results also in terms of area under curve. So it was a good solution that we didn't consider before, and that could be implemented also in research. So we could apply transformer-based solutions, generative large language models, but also the ensembling of multiple approaches for a specific task. And here there is also a detail about the ensembling. For example, we used the max method. So in this case, the ensemble prediction was just the one with the highest confidence among the two models. And here, for example, we have the weighted approach, where the ensemble confidence is just a weighted representation, the combination of the two models, where the weight was in an experiment the area under curve, and in another experiment the F1 score. So the natural language processing can present specifically in healthcare different methods for implementation and different adaptation techniques. And for us, choosing the best approach is really challenging, and it depends on the task, on the resources, on the time that we have to annotate training data. But however, it still remains a very interesting research field where it allows us to build base knowledge, and to make research also in predictive modeling and decision support system, because the data extracted through natural language processing can be then used also for downstream tasks. Thanks for the attention, and these are also the QR code for the paper and for the
question. I have a few questions. Maybe I didn't get it. Can you go back to slide 38? Because you said that the smaller set gives you better results. Is this that because you made like a specific sampling of the data, or?
Yeah, exactly. In the training set, we try to keep a balance over all the data sources. So making that in the training set, we have a good representation of all the three data sources that we used in the project. So clinical diaries, historical data, and radiodiagnostic reports. But we also use the topic analysis in order to keep inside the 550 samples a good representation of all the metastasis categories. So in this training set, we have a good representation of all the expression of metastasis that can be found inside text. So on this way, the model can know and can be trained to recognize the metastases in all the different expressions that are reported by physicians.
And so in the bigger one, you didn't...
In the bigger one, the sampling was the same, but we just increased the sample of each category. But we noticed that the results didn't improve, maybe because just the few data that we used in the first setup were sufficient to train the model and to make the model learn from the information that we gave. So in this case, one finding was this. In the other case, we also find that the few-shot learning allows to the models to learn from few data. So this is also another reason why often, also in other researches, shorter and smallest training set can help better in entity recognition.
Yes, can I add some
Yeah, of
words?
course.
And about the training set, it was also balanced between positive
And negatives.
and negative sentences.
Yeah.
And maybe there is a topic, the little one, a topic categories
Yeah.
that has not enough
Familiarity.
sentences in the bigger one. And so there was a little unbalancing in the bigger one.
Yes, exactly.
And this
Yes.
it was the reason,
For
yeah.
example, in the
CNM.
550 sentences, we consider 50 sentences for each category, and in particular 50 for high metabolic activity with positive sentences, so presence of high metabolic activity. Other 50 are about the absence of high metabolic activity, and so on for each category. The last category that has not negative expressions is the familiarity, that is another category addition to this kind of semantical expression that are the familiarities of the patients about the breast cancer metastasis. So, for example, the familiarity doesn't mean that the patient has metastasis, but we have trained the model also to recognize this kind of situation in order to exclude the familiarity from the metastasis classification.
Okay. And
Because you can find the sentences on familiarities. For example, father has metastasis, and those is a sentence positive on metastasis,
Yeah,
but
but
it's
not
not for
for
the
the-
patient.
Yeah.
okay. Another question. You said few-shot learning, so
Yes.
you are like using an already pre-trained LLM.
Yeah, exactly.
This one.
We use the sentence transformer for the multilingual, I think.
Yeah.
I don't remember the name, but I can send you.
Okay.
And it's just a sentence transformer that is available in a pre-trained version. So we didn't pre-train the sentence transformer. We used an already available one, and it's easy to insert it inside the set-fit framework. So we just find in Hugging Face all the possibilities in order to find sentence transformer that were suitable for the set-fit pipeline.
Okay. Last one.
Yeah.
On slide 48.
Okay, just a moment.
You signed all the
I'm
numbers.
impressed. Yeah. This?
The other one.
No? This?
No, before. Sorry.
Ah,
This
sorry.
This one. Okay.
Okay.
Second.
Next one. Okay. This one.
Okay.
You are talking about good explainability from training set, but
Si.
I didn't get it. And another question that is connected to this one is you say that the manual effort is lower here, but like in context learning, you need a person that write the prompt to the LLM.
Yeah.
I think it's quite stressful. Like this is your data, answer like this. So.
Mhm.
What is the difference, the big difference in manual effort between the two versions?
Okay. First question about generalization. The explainability, sorry. The explainability in the pattern matching is really high because we build the rules based on keywords and patterns that are given from physicians. So explain to physicians why the system extract information about a symptom is easy because they can recover the keywords and the patterns, and based on the text, they can find why the classification was made. In the transformer and the large language models case, the explainability is given by the training set. So, for example, if I train a BERT model with a specific examples of expressing a certain symptom, I can also say to the physician why the model make a certain classification, because that example was also represented in the training set. So the scope is always use an extensive training set that is very representative, that could contain all the possible expressions of a certain category in order to achieve and to know why, to understand why the model could have that classification. Usually the control on the training set and making the representative of the training set could help to explain the output of the model. And the same for the large language models, but in the prompting case, the training set didn't exist. I mean, in the context learning, we just make a prompt where we insert some examples, okay? For example, in here, we just giving the prompt a list of all the possible terms related to the symptoms of the lupus pathology. And in here, so we can say that if the model make a certain classification, it's highly probable that he made it based on the sentences and on the examples that we gave as input inside the prompt. So this is the sense of the explainability that we have noticed together with physicians when using this kind of models.
Okay. Question.
Yeah.
Sorry, Lilli,
Yeah?
I lost my glasses, so please.
Yeah,
read
of
the
course.
question.
You mentioned that MISTIC uses a few-shot learning approach with excellent results on dataset of 550 texts.
This is a question from Giuliana
Ranella. How do you think the model will perform when applied to other hospital settings? It's a good question, because with Mario we are thinking about expanding this approach not only on new data of our hospitals, but also on new outcomes, for example, by finding the disease progression inside the text, or for example, the location of metastases that are really required in other projects. So the goal now would be implement the MISTIC pipeline on new scenarios and also in other hospitals that would be easy to implement, because I mean, the fact that the training requires really few data is a novelty, is a good thing,
Yeah.
Because it's easy to implement also in other low data settings that can be present in other hospital scenarios.
Yes, maybe if I can integrate.
Yeah.
The very interesting thing to me is that in MISTIC we are using a general sentence transformer model.
Yeah.
I mean, we're just using a model that understands Italian in some ways, okay? Just to know if in a sentence there is a negation of metastasis or not. We are using it just to recognize the semantic of state the presence or the absence of metastasis. Because with pattern matching is not so hard to find the sentence speaking about metastasis. It's really hard in the rule-based setting to understand if there is a statement about presence or absence of metastasis, because the negation can be at the beginning, in the middle, and so on. And so the few short data are only to understand the negation or the statement of metastasis. And so, as the model is general for Italian, as Livia said, we just need other few annotated dataset to apply the model to other reports or other hospitals. And then I want to ask you something. If you can give to us more insight about the explainability of MISTIC. Why MISTIC is so explainable respect to others?
Yes, of course. In the MISTIC pipeline, we make classification not over the entire clinical report, but at the sentence level. So it means that if a report, for example, has at least one sentence positive to the metastasis category, then all the report, and so the patient associated, is classified as metastatic. And at the end of the process, if a physician asks to us why that clinical report was positive to metastasis, it's easy to recover the information because we just can't find the sentence that triggered the classification inside the whole clinical report. So it's explainable because we can reconduct the classification in the specific sentence that caused the classification of metastasis. And I think that is another question from Giuliana Ramella.
Yes. Let's read Giuliana's final question, please.
Yeah, of course. Are you considering integrating domain adaptation techniques? Yes, of course. Actually, the field of learning of MISTIC can be considered an adaptation approach. But for example, in the use case that we have seen in our latest work about llama and then the ensemble with BERT, we have done adaptation by making instruction tuning of a large language model. So for the LLM, we applied the instruction tuning of a large language model, and on the other hand, for BERT models, we implemented the fine tuning. So in both the cases, we make the adaptation on existing pre-trained weights, but it works pretty well. I mean, MISTIC was the best.
Yeah, in some ways, set fit is an adaptation technique using CPUs and not GPUs.
In the other case, for example, we leverage on GPUs.
And maybe we can say that we are training MISTIC on 10 cores. CPU, for 1 day.
Yeah,
so
also less, I think.
Yeah, maybe less.
And it was really impressive because it was usable in our hospital where we had not any server of this dimension. So it's useful also for low settings, real world applications.
You can do it in a notebook.
Yeah.
Questions?
Yeah.
Okay, I'm interested in the text summarization preprocessing step. Did you evaluate also the quality of the summarized clinical report, or you performed only the evaluation of the overall?
This is a good question. At first, we just make a manual validation of some version of reports. And we use the final evaluation over all the pipeline in order to evaluate also the upstream task for the text summarization. But for another project, we are implementing text summarization in another field. So always in the gynecological one, but other kind of tumors. And for example, in here, we are trying to decompose the task of text summarization, making multiple downstream tasks of information extraction. So in here, for example, we are evaluating the text summarization by looking at the performance of the extraction for the single components of the summary. But there are also other metrics that can be applied on the screens in order to compute, for example, the performances of the summary. But in this case of the breast use case, we didn't use an evaluation specifically for the text summarization.
Okay, maybe when this new work is ready, I would like to read it because it is important for my project and I'm trying to figure it out how to implement this part.
Thank you.
What are the main limitations on why you can't use the MISTIC pipeline on other hospitals' reports?
Main limitation? I don't want to say that, don't insist, but I mean, some hospitals don't have electronic health records. I mean, we have to work on digitalized reports, of course. So this could be a limitation for some hospital settings, and we need also the supervision of physicians. For example, the semantics can be changed also based on the physician that writes the report. So if a physician of other hospital supervise the work, saying, for example, indications about all the semantical expression that can be used for the metastasis could be useful in order to bring up the project. And so it could be a limitation if the physicians doesn't support the work. But I think that the computational point of view of MISTIC, the fact that can be implemented in a low research setting, it's really near to the necessity of a real world hospital scenario where usually I swear that there are not machines so big to implement large language models and high computational techniques. So this can be really a good thing to be implemented also in other hospitals. And actually, we are trying to implement it also, as I said before, on other outcomes. Because, for example, changing the training set that is composed by few data, and for example, giving examples about the disease progression, it could be a potential instrument in order to identify the disease progression of the patient that is usually defined in a different ways. It can depend by the treatment change. It can depend on the characteristics of the tumor. So it can be used for a lot of outcomes, and it could be really interesting to implement also in other kind of studies. So we will come back here with
so I think the good thing is that transformer is a compromise, because I mean, compared with pattern matching, of course, you are not constraining yourself to very specific strings. On the other end, because you control the training set a bit better than what you would do with the prompting, I mean, you could probably understand in another hospital how to modify the training set. And then maybe, you know, there are these techniques which are called the federated techniques, where you can use the same algorithm in parallel in different sites. So I think there is a good potential in that regard.
Yeah, another thing is that if you want to see, for example, is a new outcome, so maybe you need to see something new in the reports. For example, there are some things like non-alcoholic, how to say, non-alcoholic on the liver.
On the liver, non-alcoholic heart disease.
Yeah, there is a lot of radiodiagnostic clinical text with people not stating precisely information about radiodiagnostic, not alcoholic disease, but you can find it because the clinician knows the semantic. You can define few rules. You can just select the sentences. You can classify them. How to say? You can do a first classification about this new problem, and then state, okay, there are some people that now are positive to this kind of diagnosis. Then I can call it. I can do some hard diagnosis, but you are just using the reports, not to do new exams and so on. Okay.
Just a comment. Maybe what lupus alberto is not the name of the pathology, I guess.
No.
But this is a rhetorical question. So, from what I can see, I didn't understand too much. Actually, this is my fault. So the question is, but in this field, do you have, for instance, a formalization of how difficult is it? Can be cast in the framework of computational complexity? So can you say that some of this problem is anti-hard, anti-complete, or whatever? Is there a theory dealing with this problem?
Okay. I think no. I think
because I don't see when you
can say maybe.
maybe.
When you compare, so it seems that here it applies a paradigm known as no free lunch theorem, which means that when you have an anti-hard from the computational complexity viewpoint problem, and you know meta-heuristics can outperform any other, because on some instances an algorithm performs better and in some worse. Do you have something like that to assess how good are your So it's
Well,
for
I mean,
instance,
I know.
what does it mean?
The backend of all this.
Evaluating the quality of.
Actually, we usually evaluate the capacity of the model to recognize the domain. So we just look at the performances at the end of the implementation, basing a gold standard, so manually annotated by physician, and comparing this gold standard to the prediction of the model. So this is our approach in order to evaluate the performances of this model. And actually, I don't know if also specifically in the healthcare scenario, we can also correlate this kind of evaluation to this problem. And about the other question, Lupus Alberto, why? Because here we fine-tuned a model that is called Alberto, that is a BERT-based model adapted for the Italian language, specifically on a Twitter dataset. So we started from these checkpoints, and then we use them in order to make a fine-tuning specifically for the lupus domain. This because we found that using a model, also if not for the medical domain, but for the Italian language, was useful to achieve better results with respect to other solutions by using, for example, other kind of BERT models, multilingual, and so on. So this is just the reason for the...
Maybe I want to add something to you. Yeah, because you are speaking about a space mission to Mars, and we are just starting working from here to La Sapienza University. So what we can do is try to find some technique to control the data. I mean, sometimes textual data is not well defined, because as we see as human.
Yes, you're right, but pattern matching, I think it's very easy to define.
But it's not working. Yeah, the point is not working well. It's not working fastly as you want.
I think it should be, I think it was given for granted, but for transformer, I guess, but for sure for LLM, the model behind is recurrent neural network, which means that you may expect that this is a very complex landscape of local minima. So maybe jumping to the fact that it's NP-complete or not, then I agree with Mario. We are like from here to, I don't know, Piazzale Aldomoro, and we need to reach Milano, right?
Yeah.
But it's true that most likely we are in an NP-complete space, but we don't know, with reference to the specific semantic task, we don't know how complexity scale up. That's something that, unfortunately, as Livia was saying, we will learn it by doing. And by the way, I mean, summarization is a different thing than classification. So this is a number of different parameters. But you are right that we need to have a bit control of computational complexity when we progress.
Just to communicate.
Yeah, yeah. For example, splitting in sentences is a way
to have more control.
Yeah.
Thank you for the attention. See you next
Yeah.
time.